Today we're going to look at the second method of hypothesis testing, which involves rejection regions and critical values. Now this is the more traditional method. We have seen this for years and years, and so what you're going to find is that a lot of the steps are exactly the same as the p-value method, except they're in a different order. So with this rejection region, what we're trying to find is the range of values for which the null hypothesis is not probable. If your test statistics falls in that region, we will reject our null hypothesis, and it's a critical value that's going to separate your rejection region from your non-rejection region. All right, so to find that critical value, it all depends on your level of significance, your alpha. So if it's a left-tailed test, you're going to find the area that corresponds to alpha. Right-tailed will be on the right side, and two-tailed, you're going to have to take out half of alpha for both tails. So if I give you a two-tailed test, drawing the bell-shaped curve, putting in two tails, that alpha is for both tails. So we've got to make sure that we divide alpha by 2 so that we get the same amount for both sides, which in this case would be 0.025. Then going to your table and reading it backwards like we've had to do several times, you should find that your critical values would be positive and negative 1.96. So depending on what type test you have, if it's left-tailed, right-tailed, or two-tailed, if your test statistic falls in those tails, then you do reject your null hypothesis. If not, we fail to reject. All right, so looking at your steps here, we still want to make sure that we know that we have the population standard deviation or that our sample size is big. You're still going to state the hypothesis. You still need to find alpha. But then you're going to find your critical values by reading your table backwards. Once you get your critical values, you're going to use the same formula to find your test statistic. You'll put that test statistic on your graph and then make your decision whether or not to reject or fail to reject based on where it falls. Let's look at an example. Employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $68,000. A random sample of 30 of the company's mechanical engineers has a mean salary of $66,900 with a standard deviation of 5,500. At alpha equal to 0.05, test the manufacturer's claim. So we still have to write our hypothesis. So if you'll look, it says that they claim that it's less than the 68,000, so that's going to have to be your alternative. So that means your null is going to be greater than or equal to the 68,000. They tell us that alpha is equal to 0.05. So those first two steps were exactly the same as when we were doing it with the p-value. Now here's where it's different. We got to find our critical values. All right, drawing my bell-shaped curve. Looking at my alternative hypothesis, we see this is going to be a left-tailed test, and that alpha being 0.05 will all go in that left tail. So looking in the body of the table, reading it backwards, we see that our critical value is going to be negative 1.645. And remember, if it's exactly the same distance between two z-values, you do have to average them together to find that critical value. So now we'll find our test statistics. Same formula that we used with our p-values. You're going to take your mean minus your population mean, divide it by the standard deviation, divide it by the square root of your sample size, and you're going to get negative 1.1. Now you need to put that negative 1.1 mathematically correct on your graph. So if you're saying that this is negative 1.645, then negative 1.1 would have to be to the right of that. And that is in the area, that is not in the tail, that is in the area that we fail to reject. Let's try another one. U.S. Department of Agriculture claims that the mean cost of raising a child from birth to age 2 by husband-wife families in the U.S. is $13,120. Random sample of 500 children has a mean cost of $12,925 with a standard deviation of 1745. At alpha equal to 0.1, is there enough evidence to reject the claim? So again, first step is still to write your hypothesis. Looking at the claim, they tell us that the mean cost of raising a child is $13,120, so that's your equal sign. Alternative then would be not equal to. Your alpha is 0.1, and so now we got to find our critical values. Looking at our alternative hypothesis, this is a two-tailed test. So that means that alpha of 0.1 has to be divided in half, divide by 2, so that you get two equal parts, which would be 0.05. Then going to the body of your table, getting as close as you can, you would get 1.645 and negative 1.645 again for your critical values. Now we find our test statistic using our formula, sample mean minus the population mean, divided by the standard deviation, divided by the square root of your sample size. Putting that in your calculator, you should get a negative 2.5, and then taking that negative 2.5 and putting it correctly on your graph, it falls to the left of your critical value. So if it falls in that tail, that tells us we're going to reject our null hypothesis. So now we need to look at what do we do when our sample size is not big and we do not have our population standard deviation. We're going to have to use the t-table. The t-table is written so that you have to look at your level of significance. And if you'll remember, you had 3 rows at the top of your t-table. We are now looking at the second and third row where it says one-tailed or two-tailed. So we're going to have to determine if it's left-tailed, right-tailed, or two-tailed, and that will tell us which row to look at. And then, of course, on the left-hand side, the degrees of freedom is still n-1. All right, so if they ask us to find the critical value T0 for a left-tailed test, given alpha equal to 0.05 and n equal to 21. So that tells me my degrees of freedom would be 21 minus 1, which is 20. And then since it's left-tailed, that is a one-tailed test. So you're going to look across the top and down the side. You should find that your critical value would be negative 1.725. And again, being negative because they told us it was a left-tailed test. If they ask us to find the critical values, negative T0 and positive T0 for a two-tailed test, given that alpha is equal to 0.1 and n is equal to 26, again, to find the degrees of freedom, you subtract 1 from your sample size, which would be 25. It's two-tailed test, so you're looking at the top underneath two-tailed. Going across for alpha equal to 0.1, you should find the critical values to be positive and negative 1.708. So if we were doing a hypothesis test and our sample size is small, less than 30, and the population standard deviation is unknown, we're going to follow the same steps, except we're going to use the t-table instead of the z-table. And if you'll notice, your test statistic does use even the same formula. So everything's the same except for you're using the t-table instead of the z. So if you'll look at your steps, you're still going to state your hypothesis. You're still going to find alpha. You're going to have to find your degrees of freedom. You'll have to find your critical values. Then you'll do your test statistic and put it on your graph, and then make your decision. So let's see if we can do this. A used car dealer says that the mean price of a 2008 Honda CRV is at least $20,500. You suspect this claim is incorrect and find that a random sample of 14 similar vehicles has a mean price of $19,850 and a standard deviation of $1,084. Is there enough evidence to reject the dealer's claim at alpha equal to 0.05? Assume that the population is normally distributed. Now, if you think about it, on all our problems when they ask you to find the p-value, they say p-value. So if they don't, they're expecting you to use your rejection regions. So here we go. First thing, we've got to write our hypothesis. The claim is that the mean price is at least $20,500, so that is greater than or equal to. Alternative would be less than. Your alpha is equal to 0.05, and your sample size is 14, so your degrees of freedom would be 13. So, drawing that t-distribution, it is a left-tailed test. Go into your t-table. For one-tailed, degrees of freedom 13, alpha equal to 0.05, you should get your critical value to be negative 1.771. Now, plugging into your test statistic, you would get your mean minus the population mean divided by the standard deviation divided by the square root of your sample size. When you calculate that, you should get a negative 2.244. Now, if you put that on your graph, it falls to the left of your critical value. It falls in your tail, so that tells us we're going to reject the null hypothesis. One more, an industrial company claims that the mean pH level of the water in a nearby river is 6.8. You randomly select 19 water samples and measure the pH of each. The sample mean, standard deviation are 6.7 and 0.24 respectively. Is there enough evidence to reject the company's claim at alpha equal to 0.05? Assume that it is normally distributed. So again, first step, we got to write our hypothesis. They tell us that the mean is 6.8, so that means the alternative would be not equal. Alpha, they said, was 0.05, and since our sample size was 19, the degrees of freedom would be 18. So drawing our t-distribution, looking at your alternative hypothesis, it is two-tailed. So you're going to your t-table, looking underneath two-tailed, alpha equal to 0.05, degrees of freedom of 18, you should get your critical values to be negative 2.101 and positive 2.101. Now, computing your test statistic. Take your mean minus the population mean over the standard deviation divided by the sample size. You should get a negative 1.816. Now, if you put that on your graph, you see it falls in between your critical values, not in a tail, so we will fail to reject our null hypothesis. Now, if you'll look at this example, they say to use p-values with the t-test. In order to do that, it's going to require you using some type of technology. So for those of you who have graphing calculators, great, you can work the problem. If you had some type of statistical package, you could work it. But we don't require that in class. So we cannot work this without some help. So I show you all of this because I do want you to omit any problems on your homework that asks for you to use the p-value when you're having to use your t-test. Just omit those, unless you want to try to work with technology, but omit them. Don't worry about them. All right, so we've got one more hypothesis test that we need to look at, and it is with our population proportion. It can be used when your binomial distribution is such that n times p is greater than or equal to 5 and n times q is greater than or equal to 5, which will always happen, so we're not going to worry about having to test that every time. Now the test statistic is p hat, and notice your formula changes because we're dealing with proportions instead of the mean. So your test statistic formula would be p hat minus p divided by the square root of p times q divided by n. Now make sure you notice that square root is over everything in the denominator. So when you type this in, you're probably going to have to put parentheses around the top and underneath the radical to make sure that you get that typed in correctly. All right, so notice your steps. They're exactly the same. You're still going to have to find your state your hypothesis. You're going to have to find alpha. You'll have to find your critical values. You'll have to use the new formula for your test statistic, put it on the graph, and then decide whether you're going to reject or fail to reject. So let's look at this example. A researcher claims that less than 50% of the U.S. adults have accessed the Internet over the wireless network with a laptop computer. In a random sample of 100 adults, 39% say they have accessed the Internet over a wireless network with a laptop computer. At alpha equal to 0.01, is there enough evidence to support the researcher's claim? All right, so again, we got to write the hypothesis. Now notice we're dealing with proportions instead of the mean, so we're going to use a p as our variable. They tell us, or they claim, that less than 50%, so that would be your alternative hypothesis. Your null would be greater than or equal to 0.5. Alpha they gave us is equal to 0.01. Proportions always use the z-table, so we don't have to worry about the t-table at all. So drawing our bell-shaped curve, looking at our alternative hypothesis, it is left-tailed. Since it's only one tail, that whole alpha value goes for that one tail. Reading your table backwards, you should get your critical value to be negative 2.33. Now your test statistic. You take your p hat minus your p-value divided by the square root of your p-value times the q-value over your sample size. Putting that in your calculator, you should get a negative 2.2. Putting that negative 2.2 on your graph, it's close, but it's still to the right of your critical value, so we're going to fail to reject that null hypothesis. One more. The research center claims that 25% of college graduates think a college degree is not worth the cost. You decide to test this claim and ask a random sample of 200 college graduates whether they think a college is not worth the cost. Of those surveyed, 21% replied yes. At alpha equal to 0.1, is there enough evidence to reject the claim? So, writing our hypothesis. They claim that 25% of the college graduates think it's not worth it. So, your proportion is equal to 0.25 and not equal to 0.25. They told us alpha is equal to 0.1. So to find my critical values, this is a two-tailed test. If alpha is equal to 0.1, I got to divide it in half since there's two tails. So each tail would get 0.05. Looking in your table backwards, you get the negative 1.645 and positive 1.645. Now, using your test statistic formula, take your p hat minus your p, divided by the square root of p times q over your sample size. And when you calculate that, you're going to get a negative 1.31. Now, putting that on the graph, it falls in between your two critical values. So that tells us we failed to reject the null hypothesis. Now you should be able to work all 6 problems on your worksheet now using the rejection regions, your critical values. Work those and check them.